Late, just so you know. Hello, everyone, and welcome. We are here with Deep Learning Indaba for the Indaba Grand Challenge practicals. So this Indaba session is about showing you guys what you need to know to be able to do this practical session, to do the challenge in the best way possible, and to be able to get the most out of this challenge. So with us today, we have obviously our lovely panel of awesome people. I am just here as a moderator. So we have our own Martin Squark from Indaba. We have Echo Duker from Zindi. We have Nicolas Lopez Carranza from Indaba. And we have Kerim Gir from Deep Learning Indaba. If at any moment you guys feel that you want to ask a question, please don't hesitate. Just write it down in the chat, and I'll be able to put it up for our panel to answer. Okay? So I'm going to eclipse myself, and I'm going to leave you guys with our dear panel. And I hope that everyone has fun and learns the most possible from the session. I'm just opening up the presentation, and I am off.
Cool. Thanks a lot, Zora, for the introduction. And so yeah, today it's all about the practicals and answering your question regarding the Grand Challenge. But before that, maybe for those who are not familiar with the Grand Challenge or Indaba, we just wanted to give you like the context of this competition or this like collaboration, across countries in Africa and beyond. So Zora, I don't know if you can share the slides. Here we go. Super. Okay, so basically, if we go to the next slide, just to give you a little bit an idea about deep tech disruption and the opportunities it gets in the world and how this relates to the Grand Challenge. If you look at AI and data-driven innovation in the world, this is something I was mentioning recently at AI Expo. But really, like in the US, innovation is driven by the tech giants, Google, Microsoft, Facebook, Amazon, Apple, and others. In Europe, it's all about individual and privacy rights and technologies related to it, such as homomorphic encryption and other. In Asia, the driver of progress is mostly, this innovation is led by governments. But if you look at Africa, it's interesting to understand Africa's strength and what we can do together. So if we go to the next slide, we believe actually that the strength of Africa are in startups and communities. We have large established communities in machine learning, in deep tech, that allow us to do new things. And in particular, the Grand Challenge is one example. And we also have innovative startups that are emerging. And so I firmly believe that this is Africa's opportunity and that we can do things that are daring and new. So if we look at the next slide, the idea of what we're doing here is that through the Indaba, which is the largest machine learning community in Africa, we have the opportunity to collaborate. We have the opportunity to strengthen machine learning and AI, and this is all across all fields, whether it's languages or in this particular case, bioinformatics and healthcare. In every sector, literally, there is an opportunity for the Indaba to show what can be achieved and to promote Pan-African excellence in machine learning and AI. And in particular, if we look at what the Indaba has been doing in terms of events, on the next slide, you will see that it's already quite, like a widespread organization in the sense that we have Indaba Access across in 2019, 27 countries. And this is in constant growth with thousands of attendees. So I believe this is Africa's opportunity. There is an opportunity for us to work together, to collaborate, share best practices, and as a consequence, tackle problems which until recently were science fiction, such as curing leishmaniasis, which is the goal of this grand challenge. So if we look at, what is the challenge there on the next slide, and what's the situation in the world today, there's a large class of what we call neglected tropical diseases, which are literally diseases that big pharma groups do not have the bandwidth or, which are not priority enough for big pharma groups to process. And as a consequence, there is an opportunity for the community, and through all the knowledge and data which is available today freely in the world, to make a difference and in particular save lives. Leishmaniasis is a parasitic disease that kills dozens of thousands of people a year. And in many ways, it's all about finding the right existing drug, which we call drug repurposing. And if we do that across all the data which is freely available, we might have a chance to cure the disease and save lives. And I think this is super exciting, because this is the kind of opportunities that did not exist before, that are now possible through wide availability of data, but also self-organizing communities such as the Indaba and different startups which are collaborating with Indaba, such as, for example, Zindi, from which Echo, one of the co-founders, is present today, with Indaba, with InstaDeep volunteers as well, who are present on this call. So there is a chance to really build up a new way to do innovation. And I think it's particularly appropriate in Africa, given our strengths in community and also the existence of vibrant startups. And so if we look at the next slide, the goal of what we are doing today is really to break new ground. First, save lives, but empower our community. Deep tech innovation can happen in Africa, and it can really crack problems that we do care about. And at the same time, we can showcase different ways to do machine learning innovation in complex fields such as bioinformatics and life sciences. And so this is what it is about today. And we've been very honored to receive a lot of support for this initiative, including from the World Health Organization, which expressed a lot of interest and encouraged us to push forward. And so today, the goal is really to get into the details and get you to participate and collaborate in this landmark event. Before we do that, I also wanted to thank all our partners, which are on the next slide, who are key to having made this event possible. So, IDRC, CRDI from Canada, SIDA, Knowledge for All, obviously InstaDeep and Zindi. Those are the organizing partners. But we also received significant support from, different, either computing partners such as TensorFlow and Google, but also large communities such as Data Science Africa, Data Science Nigeria, Black in AI, DSNA in North Africa, Alliance for AI all across the continent. So it's thanks to, our ability to collaborate that we can really break new ground. And I think this is quite exciting. So this was to give you sort of a quick context. We're very happy to get into the details. And so in terms of, the practicals today, we're going to have Dr. Marcin Skwark first explain, the problem and walk us through the practicals, together with Nicolas Lopez Carranza, who's another volunteer from InstaDeep, who's been working on the platform and making all this happen seamlessly. Echo Ducker from Zindi will also explain to us how Zindi functions and how you can submit your solutions to the Zindi platform. So everything is in place for us to make progress on this great challenge. And without spending more time, I'm very happy to introduce Dr. Marcin Skwark, who's going to tell us more about the practicalities of the Grand Challenge. But importantly, don't hesitate to ask questions. You have, the channel, the comments channel to put questions there, and Zora will pick them up. So don't hesitate. It's meant to be an interactive event and a chance for you to ask all the questions you have in mind. So there are no stupid questions. All questions are welcome. So Marcin, up to you.
So hello, everybody. I'm very happy to talk to you today, and I really hope it's going to be a bi-directional communication, because I do realize that the whole challenge is relatively daunting. There's a lot to do. There's a lot of data to tackle. There's a lot of methods to employ, and I do know that hardly any one of you is a computational biologist, and you don't need to be a computational biologist to tackle this challenge. Hopefully today I can give you at least a few starting points that we can build on to be successful. I know that a lot of you had questions and problems, and I'm very happy to answer all of those. I believe I had a slide somewhere that we can talk about later on. But practically, the challenge can be thought of in one of two ways. One, the way that Karim has mentioned, drug repurposing. There's so many different small molecules that are already approved that we can use to try to treat leishmaniasis. And all that it is really pattern matching. It's finding if a particular molecule or a similar molecule has already been shown to work on a particular protein or a similar protein. And today I'll tell you a bit more about how to do similarity comparisons, how to find analogous or what we call homologous proteins that originate from the same evolutionary source, how to model the structure, how to do the docking of one onto the other. Pretty much, I'm going to give you a master's degree worth of cheminformatics and bioinformatics in an hour or two. Well, maybe not exactly, but I'll try to do my best. But that's just one angle. The other angle, which is also super exciting, at least exciting for me, is identification of new drug targets. Because we know that certain drugs work on particular drug targets, but there's so much work on off-target effect. The fact that a small molecule can bind to its target, but also can bind to something else. And hopefully, by binding to something else in the parasite, it will kill it or it will make it less fit. And we don't really need to kill the parasite. All that we need to do is make it a bit weaker, make it stay a bit longer so that the immune system can tackle it. Or that it gets outcompeted by something that's not as dangerous to humans. So all of this we can do. I don't know if I should get started with the practicals, or should we rather move to Nicholas and Echo, and then do start with the practicals. What do you say, Karim?
Maybe Echo can say a few words about Zindi, and then we'll deep dive into the practical.
Mm-hmm.
Yeah.
So thank you very much, everybody, and I'm very pleased to be here. So maybe we can just go to my first slide, and I'll say a few words about Zindi and what Zindi does and why we started Zindi. Right. So we started Zindi 2 years ago, in September 2018. And in a pretty short time, Zindi has pretty much become the machine learning marketplace for the African continent. So you may be asking why we started Zindi, and the answer is quite simple. And I think you'll see this on the next slide. So according to the World Bank, more than 80% of global population growth by the turn of the century will come from the African continent. So we can expect that the demand for everything, from water to schooling to healthcare, will rise exponentially. So by the turn of the century, 1 in 3 people pretty much will live on the African continent. So I think it's not a big stretch to imagine that the fortunes of Africa will play a big role in the fortunes of the world at large. And I think we've seen this especially so this year in 2020 with the pandemic, that I think it's fair to say that without bold and creative solutions, such as the Indaba Grand Challenges it has been setting out, the future of Africa and indeed the world will be at risk. So that's So that in a nutshell is why we started Zindi. Next slide, please. So Zindi, like I said, has grown very quickly. So at the moment, we have more than 18,000 registered users. Most of them come from the African continent, but by no means all. And Zindi is the first and the largest community of mostly African data scientists, solving what we like to call the world's most pressing challenges using AI and machine learning. And certainly, the race to find a cure for leishmaniasis is certainly one of these. And on the next slide, we'll see the value proposition, or how we describe the value proposition for both sides of the marketplace. So for data scientists, they get the opportunity to test their skills. They also get the opportunity to learn by doing, such as you will be doing here. They also have an opportunity to earn some income by doing what they enjoy and they do best, and also helps them to build their profile. And I know that for some people that's important. But I think above all, the Zindi proposition to data scientists is that it helps you solve problems that we like to think really, really matter. And then for the organizations on the next slide, the proposition for them is around essentially finding the best solution to the challenges you face. And you're also able to get in touch with the best data scientists who can solve your problem. So that essentially is why we started Zindi and what the proposition is to both sides of the marketplace. And on the next slide, we summarize what Zindi is about. So Zindi is essentially a platform, and it matches your talent to existing needs. So we look forward to working with you as you bring your talents to bear on what is an extremely important problem that I believe has simply gone unattended for much too long. So thank you very much.
Thank you, Eiko, for presenting Zindi, and importantly for your your support and contribution to the Grand Challenge. It's thanks to Zindi that we can organize this event in a completely decentralized way, meaning that anybody in Africa and beyond can participate, can submit solution, and ultimately can have fun, learn, and hopefully contribute to save lives. So Marcin, we would love to hear more about how we can do this and how to code and get going. Yeah.
Right. So we have there are a few ways to start on the challenge. The data that we've shared with you consists of all of the proteins from all the Leishmania species, at least the ones that are known to be detrimental to humans. Each of these proteins could technically be a drug target. If you find a small molecule that targets more than one of these proteins, the better. So the first thing that you may want to do, that perhaps you maybe I can share my screen somehow. Okay. Application window. Okay. And hopefully you can see me now. So one of the best resources to start from is UniProt. It's you've been given sequences that have been derived from UniProt for each and every known Leishmania protein, and but you can also search for one of all the Leishmania proteins just by full-text search. You can search by organism. Let's assume that we want to look at just the Leishmania major, one of the eminent Leishmania species. And what we see here, that among others, is that there's 8,500 proteins, but only 69 of them are reviewed, which means that only 69 of them are the proteins that, for which the existence of the protein is confirmed, that it's and there's some sort of experimental data for it. Let's look at all of them. Okay, and for each of these, we get the names, gene names, but each of these has an answer, and let's pick this one for example. Just at random, and you can get loads of interesting information about that. By the way, all of that is downloadable also as JSON files, XML files. There's a RESTful interface to UniProt, so you don't have to do any searches for the website. But the website is much more, much nicer from the visual point of view. And the protein that I've picked here is a nice one because it's well annotated as experimental evidence at the transcript level, which means that the protein actually, at least the gene, gets expressed in the cell. But what we could be interested in the function and which biological processes the gene is involved in. But what we may want to look at is somewhere below here for a type called structure, and I'll be covering ligand-based drug discovery later on. But first and foremost, you may want to what really matters is if the small molecule you come up with fits into the binding pocket of that of the protein. And a lot of proteins have already computed models or even experimentally resolved structures. So let's see if there's a structure in Swiss model resource that actually has that's some. And yes, there is one with relatively decent, with feasible quality. You could get the model rebuilt, but well, we're computational scientists. We're not biologists, and we're not afraid of doing things ourselves. So what we could do, while I'm showing you the rest of the data that can be gotten from UniProt, is we can try to build a model ourselves. So what I did now is I went to the sequence tab and opened the text file, which contains the protein sequence. Exactly the same way as same sort of a sequence as you would get from the data shared with you on the Indaba website. And there's plenty of different resources that can do protein structure prediction for you online. One of my favorite ones is HHPRED, developed in Germany, in Tübingen, and so I'll share with you the link to it later on. And the reason why it's one of my favorites is twofold. One, it's open source and freely available. Second, it's actually well written and it works well enough. Here I'll run the method online, but I'll just click submit so it starts running. But it's also available as a GitHub repo. Not only you can check it out from GitHub, they also provide the conda package and the Docker image. So there's nothing that precludes you from running it on your own site. What the method does is first identifying the other proteins that are evolutionarily related to your query, then building a statistical model of these that tells you which positions are more or less important from the evolutionary point of view, and then using this model to query a database of templates of protein structures, of proteins with known structures. And this thing will take around a minute, maybe 3. But it's going to get us a page that looks sort of like this one. So it contains the history of different different structures, and importantly enough, you can also build a model just using either the structures we have picked or what is the first hit. And all that you need to do is just click forward, 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 and off it goes. Well, here you would need to enter the key, and as we're doing, as our operation is entirely non-profit, there's no harm in me sharing the key with you. It's you can get it from Modeler's website that I'll show you in just a moment. But that's all that needs to happen. Modeler itself has been developed at the University of Cambridge, but now it's being developed at UCSF in California, and you could download it after registration and run it on your own computer. There's actually a pretty decent tutorial that teaches you how to use it. In case you don't want to use the online resource, or if you want to do the modeling on your own machine. The thing here is that Modeler is also available. Actually, it's available in most of the Linux repositories. There's a Conda repo there. I believe you can install it with pip as well. So both Modeler and HHPred are freely available, and there's getting them to run requires effectively two lines of commands: conda install Modeler, conda install HHSuite. And hopefully our model is ready here. So that's the PDB file that for our new structure, and all that we need to do here is now just click down PDB file, and here it is. That's
just wanted to mention we're putting the link to the modeler just there at the bottom of the screen. So this is entirely free. So don't hesitate to go on that link, and you have all the tutorials about how to use modeler. But basically, this allows you to get going, as Martin is showing, very quickly and for free. So you just need an internet connection, which is cool.
Yes. So both HHPred and Modeler are, as Karim said and I said, free, and they're relatively efficient compute-wise. There are methods that are more computationally intense. There are methods that are perhaps more accurate, but the beautiful bit here is that for so-called easy homology modeling, the modeling in which you have close templates available, it doesn't really matter what tools you use. Well, at least if you use the standards compliant modern tools. And with Modeler, you can build thousands of protein models in a day. On an 8-core machine, I was able to build around 6,000 models a day, which is quite feasible. So we've covered the way how to produce models on your own, but let's get back to the to UniProt. So even if there was no structure available here, we could model the structure ourselves, either through the online resources or download it from an online database. But that's not all. What we could do still is we could look at the annotations. We can look, for example, at the Gene3D package that I'm resource that's a part of CAP nowadays. That can tell you all about. Hopefully, it will open sometime soon. It will tell you all about the species that proteins containing this domain are found in. So here we see that it's mostly bacteria, plants, and fungi, and there are a few eukaryotes, which is good. That means that it's perhaps not really hopefully it's not that important for humans. And we could look at a lot of interesting things here, including the sexually related proteins that I cannot now.
Martin, also, I think we have a question from Hussameddin Othman. So, hello everyone. Are there any estimations about the number of druggable proteins in Leishmania species?
Yes, that's a very good question. It's I haven't done an estimate of like that myself, and the question it really boils down to a question: what do you mean? What does one mean by a druggable protein? Because if a druggable protein is a protein that can be targeted by known drugs, I believe there's quite a lot of these. But if a druggable protein is a protein that's that can be targeted by known drugs, and these drugs are not non-toxic to the host, there's fewer of these. Then there's a problem of the drug transport into. Maybe I can stop sharing my screen for a moment. There's a problem of drug transport into the parasite, which is once again a bit of a problem, and we don't have good models for that. So, but I would. So we have 18 known drugs that kind of most of which we don't really know how they work from the molecular point of view. But I think that there should be tens, if not hundreds, of proteins that could be feasible drug targets in any particular Leishmania species. It's purely it's a pure guesstimate, but it's one. It's actually. Let me share the screen again. Application window. So let's actually see what we can find about Leishmania in DrugBank. DrugBank is a really nice resource. It's drugbank.ca, or basically now drugbank.com, and it contains the information about the drugs that are available on the markets, either as approved or investigational, or we can just look at the list of drugs and experimental drugs. But all of it aims to contain information about all the molecules that have been either approved or are close to be approved for particular indications. And let's pick a random one, phentamidine, which is a beautiful drug. It's used for leishmaniasis, for other trypanosoma diseases, some fungal infections. And as far as I know, we don't know what's the mode of action of phentamidine. So, for example, if it's here it says that it's thought to interfere with the nuclear metabolism. So perhaps there's a protein in Leishmania for which maybe it's a transcriptase or some other enzyme that helps in that's important synthesis of nucleic acids. That this small molecule binds to, instead of its natural normal not compound but substrate. That's the word that I was looking for, substrate. We know that this particular molecule is not great. It causes side effects such as diabetes, so it mostly kills some of your pancreatic cells, central nervous damage, other toxic effects. So if we were able to find something that's similar to it, but not exactly like this one. Perhaps it could be better. And well, we see drug interactions here. Nothing that's particularly important for us. But what we do have here are the identifiers. We have, for example, the smile strings, which is a text description of the small molecule structure. Well, we have also the in-key keys, which are much nicer from the parsing point of view, but they're much poorer to read. But let's track this, pick this smile string, and see if we can find. There should be a link to. Well, there's a link to PubChem. Let's let me open PubChem and let's open this one, and maybe binding DB, and maybe Campbell, and sync. So there's so many resources that one can access. In particular, if we want to, by the way, Drug Bank also has machine processable data. So all of this can be downloaded in a way that's actually can be parsed by your XML parser or JSON parser. Then here we see pentamidine structures. All of these can be downloaded. Once again, they can be downloaded through a RESTful interface. So if you identify a molecule, translating between say drug bank IDs, PubChem IDs, Campbell IDs, these three being large drug databases, is quite simple, and each of these resources provides facilities to do such a translation. And I can actually download it. Yes, so you can download the molecule either as a structure or in some of the nice data formats. And technically now, what you would have is the structure of your molecule, of your protein, and the structure of your drug, and you could use these to you could try to put them together. However, let's see if I can find anything that's important for us. Well, there are plenty of properties that one can infer about these molecules, and that's one of the ways one could start. You could, for example, look at the molecules that are known to work against a particular pathogen, and see if they share anything in common. Starting from things like molecular weights, the number of hydrogen bond donors, acceptors, but mostly what you would like to learn on is the structure of the molecule itself. So the topology of the molecule, what's connected to what can be learned about the molecule. Like sometimes you have a 6-membered ring here, then you have a flexible linker, another 6-membered ring. Actually, it's a beautiful molecule because it's symmetric. And I have here a note that I'll show you with some adequate basic methodology. But before we do that, I want to show there's so much here that's relevant for us. Well, these things are not particularly relevant. But for example, log P, which is the partition coefficient, tells us how fatty our molecule is and how if it likes water or not. But I want to get here the related substances. You can also use PubChem to get the substances that are related, that are similar somehow, and you could use these resources to find what's meaningful for this particular task. Let's say it's a lot of here it is the things, but we can moreover what we can do is we can find the structures of all of the complexes in which this molecule is present. And that's another way to tackle our problem. We could take the models of our of proteins in Leishmaniasis and compare them to the known structures in protein data bank, which I thought I could actually open somewhere here, and see if two molecules share the same structure, so they superimpose well, then perhaps they would also share the binding pockets. And if they do share the binding pockets, similar drugs may bind them. So we could use this thing as a similarity metric. And so there's the human metabolome database, which you could technically use to see to learn about the toxicity. But that's the binding DB, and that's once again. All of these are available from the PubChem database. Once again, binding DB contains data that you can download freely, and it tells you how well this particular molecule. Here we were searching for this molecule, so all of these are the same. Binds to particular proteins. Here we have the diamine oxidase in humans. Actually, it seems to bind to quite a lot of human proteins. All in all, that it's loads and loads of data, and there are online resources that allow you to that teach you how to do cheminformatics. I'll show you just a tiny bit of it, perhaps here. But maybe still a better idea is to look at one more thing, and that's the protein-protein interactions. And here, for each of the Leishmania proteins, either in UniProt, we can find all the proteins that it talks to. So we could, we could try to see if a particular protein is important, if it's a hub of an interaction network somewhere, or even better, if it's if some of the proteins could be, for example, the bottlenecks in protein-protein interaction networks, and therefore, if you disable one of these, you could have a high chance of killing the bug, killing the pathogen. So I know that I'm jumping from subject to subject, but I wanted to first talk about the things that we can, the places we can start from, before hopefully delving into the things that are of particular interest for you. So we have the Campbell here. Let me just check if there's anything that's relevant. Okay, so now let's talk something that's more perhaps more familiar to a lot of us, and that's, well, let's talk Jupyter Notebooks. So the what I have done here is I've downloaded some of the anti-keratoplast molecules from Campbell, and it's so that this file here is just a direct download from Campbell of some of the molecules that have been described to have anti-keratoplast activity. Well, with keratoplasts being parasites like Leishmania or Trypanosoma bugs. And I just dropped those that would have the same ID, or well, first the same SMILES and Campbell ID, and then the same Campbell ID. And these are the things we can get from there. About the molecule ID, the assay type, etc. And the molecules in that CSV file are smile strings. The ones that have shown you. It's where's the smile string here.
Actually, Martin, is the Jupyter notebook publicly available? Maybe we
so
can, if yes, we can share the.
It is well. I've realized that I have to admit that this one is an older one, and it has it needs a few tweaks to the wording in it, but it will be publicly available. It is available in the GitLab, but it's available in the history of the in the GitLab. So I can. It's it's been it's not present there at the moment. I have, and that's my overlooking. But that doesn't matter.
But we will make a public version of it available at some point, right?
Yes, yes, we will. It's just my overlooking. What I'm going to show you here is one of the Python packages for Cheminformatics, one of the most widely used one, called RDKit. And I cannot claim to. What I'm going to show you is not all that the RDKit can do. It's not even a tiny fraction of it. It's very, very powerful, but it also has really good tutorials. And I sincerely recommend that you, if you want to go through the small molecule route and actually try to search for novel chemical matter, or to get the descriptors for the small molecules, such that that could be used as features for the machine learning model, RDKit is wonderful. So what I'm importing here is some of the standard modules, and one of those has a function called that makes RDKit molecule from a smile string. So it takes a string as an input and produces an internal representation of the molecule. We can draw them if you want to. It's fun, but most of you are not medicinal chemists, and perhaps and there's a little that you or me can derive from such pictures. But what we can do, though, is we can compute descriptors of this molecule. Because there's so much that we can do, right? One can easily tell that this one is much smaller than this one. So, like I don't know if you can see my cursor actually, but so one can tell that that they are of different sizes. One can say that one can tell if they are on that perhaps this one here has the one in the top row on the right has a fused ring, and you could compute things like, well, the molecular weight, the flexibility. You could see that this molecule, the molecule in the second row, third from the left, is fully rigid. It has no rotatable bonds, whereas its neighbor to the right, so the last molecule in the middle row, has a lot of places we can rotate. Maybe that's also important. So I can compute lots of descriptors using the RDKit descriptor module. That think molecular weight, the partial charges, the number of valence electrons in the molecule, and all of these you could then use as input features. You could, for example, see that here we have the molecular weight, and here we see so in the plot, and on the y-axis we see the how fatty or how hydrophobic the molecule is, and we see that most of the molecules are relatively they're not large, but they're not very, very small, and they're rather hydrophobic. Okay, maybe that's at least those are the ones that have been tested in that file. But maybe there's a difference between the actives and inactives. So the thing, so what I'm plotting here is the same plot, but now the color coding is the activity. I've computed computed the natural logarithm of it a few rows up, and what we see here is that there's well, we actually want to have that log value to be low, because that's the concentration that's needed for the molecule to be active. And we see that there's not that much of a correlation here. We see actives, so the deep blue dots for large sort of and hydrophobic molecules, but we also see actives for small hydrophilic ones. So it's so perhaps these features are not really good predictors, and that's true. It's especially for organisms like Leishmaniasis. The simple molecular descriptors are not really that predictive. What is predictive, though, is the composition of the molecule. So if we look at these molecules here, we can see that there's a lot of them, a lot that they have in common. For example, they have, so let's see now, they have a 6-member ring here that's present in pretty much every single molecule. Well, actually, all of these molecules have 6-member rings. Some of them have more than one. And maybe these things are important. So what a lot of computational chemistry and computational medicinal chemistry relies on is similarity comparisons. And I believe that we, as a machine learning community, can do it so much better than they do. Because all our molecules are undirected graphs where, well, actually, multi-graphs, because you can have multiple bonds between nodes. With nodes being atom types, so we have maybe 6 different node types, and you have edges or multiple edges between them, or edges with weights. And all that you want to do is you want to find, given one graph, you want to find other graphs that are similar, for which the connectivity is similar and the node types overlap. And one of the ways to do it from the cheminformatic point of view is to compute a chemical similarity fingerprint. And these are usually either enumerations of common substructures, or mostly these, represented as fixed length bit vectors. And what I'm doing here is, well, getting the Morgan fingerprints as bit vectors, and Morgan fingerprints are similar. They're based on, well, you can set how large they are supposed to be. So here they are based on fragments of 1 or 2 atom length, and the whole thing can be read here in the Wikipedia's chemical similarity article. And the more in-depth treatment of fingerprints can be seen here on the in the Greg Landrum's Adikit's author's talk. But what we can do is we can compute those similarities, and then we could fingerprints, and then we can compute the similarities. The most common similarity metric for cheminformatics is tiny motor similarity, which is the number of the intersection of 2 fingerprints divided by their union. So the length of the sum of ones in common between 2 fingerprints divided by the ones that are present in at least one of those. Obviously, two identical molecules would have a tiny motor similarity of 1. Getting a 0 is nearly impossible, but anything that's above 0.8 is a surefire hit. anything that's below 0.3 or 0.4 is most probably random. So what if we plot the pairwise similarity, we see that each of the molecules is similar to itself, of course, but then there are some molecules that are very similar to each other. It's perhaps hardly visible in this plot, but it's true. And now I'll share with you something that I never believed before I actually saw it. That's pretty much all that the big pharma does for drug discovery. It's all about similarity searches and finding what's common based on concepts that have been devised 20, 30, 40 years ago. I believe, as I said, we can do better, and I believe that's one of the low-hanging fruits. To find a better way to find similar molecules, to find similar graphs in your database. However, there's more than you can do. So we could compute other easily computable features like number of heavy atoms, number of hydrogen bond donors and acceptors, number of rings, all of which ADKit is happy to provide for you. So that's what I'm doing here. And then I'm training a very simple sklearn random forest regressor. I believe that it's the first it's the regressor that I'm training first. Blah, blah, blah. Okay, right. I'm going through all the models here. So it's okay. It's on the forest regressor only. And what we see is that my mean squared error on the training set is good, but it's on the test it's terrible. So that's R squared, and the mean square error is kind of poor as well. So what we see is that my predictor didn't really work out, did it? With R squared of minus 0.03. But well, as I said, global descriptors don't really work. So I've computed the Morgan fingerprints. Well, the ADKit fingerprint as well, just to demonstrate some more. I've added a few more machine learning methods. So a simple feed-forward neural net and some support vector regressor. And all in all, it's well, it's not particularly, it's not much better. Perhaps, none of it is awesome. However, this way, that's mostly because of the fact that I've had a really small training set, and I've didn't really pay that much of an attention to my features. However, these are the things you could start with. We have a lot of information about activity of molecules. So what one could do is you could, for example, identify. If we now identify related proteins to the one that you have. For example, let's talk about the same. We talk about this one, right? Yes, you can identify related proteins by just clicking by going to the similar proteins tab in UniProt, and I'll say with full view. We could see all the proteins that are with 50% identical or more to our query. We could there's 23 of them, not particularly much, but still, we could do that. We could find so it's very much all about similarity searches, either in terms of sequence similarity between different proteins, and then some sort of knowledge transfer, as in If two proteins are similar, they come. Then most probably they have a similar function, or and therefore they would bind similar molecules. Or so it could be either the similarity in the protein domain or the similarity in the small molecule domain. If we know that this molecule works, then the similar molecules might work as well. But as they say, proof of the cooking is in the pudding. So what we already know how to get the model of your protein, at least in one way. We know how to get the structure of your small molecule, at least in one way. Now we would like to put it together, and we have another Jupyter notebook that does exactly that. And hopefully Nicholas is still around here, and he could tell us more about it.
Hi, Martin. Thank you so much for that broad and comprehensive list of tools that we can use. Very, very interesting. I'm sure there are more tools, and we should do these sessions more often. But yeah, to give us with a taste of what it needs to be done in the last minutes, I would like to share my screen and show you the starter notebook that probably you guys already have seen. So let me share my screen. Can you guys please confirm that you can see my screen? Yeah, probably that's, yes, I will take that as a yes. Perfect. So yeah, if we go to the main challenge page, I would like to say that there is already a lot of information available. Some of the information that Martin talked about, we took the effort of converting that information, those databases, into more approachable files that you can just download and start investigating. And here we have 3 of them, but you are more than welcome to have a look at the data page on the challenge, where the data is very well explained. Also, if you're new joiners, I think that the discussions are a very good way to get involved and start seeing what the community is talking about and what's going on for the challenge. And of course, this is a challenge, so there is a leaderboard, and we are looking forward to see your name on top of the leaderboard. And in these last minutes, we would like to show you how to get that done from zero to hero, from scratch, to submit a protein structure data file into the challenge. So the starting point, and by the way, if you want to find it, you can go into the discussions. Inside there is a starter notebook discussion, and if you go to the starting point, what you can clone is a GitLab repository that has 3 notebooks, and let's have a look at the Indaba challenge one. We can clone this notebook. This is what I have done, and I have it locally cloned on my machine. And this is a Jupyter notebook running on locally on my machine, where we are gonna do the exercise of taking a protein on the Leishmaniasis parasite and trying a drug, which is a peptide, and try to dock it into it to see if it blocks. And we are gonna try to analyze the interface energy. For more data on this, we are welcome. Please, you're welcome to post the questions while we go through the notebook, and myself or Martin will be more than happy to answer it. There is one caveat, that we use a software for doing this, and the software is called Rosetta. The good news is that you can get a license for free, and it's a very, very simple process to get a license. And I would really like you guys to get you started with getting a license. So there are 2 steps for this. You go to the PyRosetta license page, which we can share on the description now. But you go there, and you will have to create an account, and then just fill in a form, and you will end up with a username and a password. That is your license. Once you have that, the easiest way to get started is to create a conda environment, and that you can use it by running the conda environment create environment.yaml, and the environment.yaml file that we have, it's available on the repository. So the only thing that you need to do is go to the environment.yaml in the repo and essentially put the user and password here that you get. And this is a free username and password. It really is for the community to help Rosetta to show this is a publicly funded project. So it's a consortium of universities. So please take the effort of going and getting a user account and creating the username and password, because it's very, very important for getting this password. Just completing it here and then creating the environment. When the environment is created, which is basically running these steps, we install the rest of the libraries, and the first thing we are going to do is we are going to take the molecule files, which is the data set that has thousands of approved drugs, a list of drugs, and we are going to download it. This is the molecules.zip. And then we also are going to have, for example, a special protein that is going to be our target. We are picking this one, which Martin, maybe you can talk more about erlotinib.
Yeah.
Okay. Yeah. Well, so this is the peptide,
but it's,
that we are going to try.
Yeah, it's
right?
a small molecule, and it's a beautiful kinase inhibitor, but it's well, it's really, really bad for you. But it's
okay, I took this one by random by looking at the data set. Like there are thousands of them to try. So I just took one by random, which is basically the molecule, the small molecule. It's not a peptide, okay? The drug essentially. And we are gonna try also this target, which again, there are so many targets. And what the target essentially is a PDB file. For those who are not familiar with the PDB files, is a crystal structure of the protein. Martin was talking a bit about it on how to generate them out of a sequence. And basically, we need to obtain this PDB file. We are also giving a lot of PDB files available for you to start trying. And what we are going to try is what we call a docking process. So a docking process will take the peptide or drug, and we'll try to dock it into the receptor. And this is done with Rosetta.
Okay.
And here, for that, we need to
for a moment. I just wanted to say that we've enclosed the statues for a lot of the Leishmania proteins. So we have thousands, tens of thousands of PDB files to start from, and we've also enclosed the molecule, the compounds. All of the approved compounds, plus a lot of experimental ones, plus a lot of other ones, and they're all named after the INTI keys, so like unique identifiers. So each of the compounds that we have enclosed, you can just take the name of it, type it into PubChem, type it into Campbell, type it into drug bank, and you'll get information on that. You'll get similarities to other molecules. So each of the PDB files, each of the statues is named by its UniProt ID. So you can take the ID, go to UniProt, and you'll get loads of information about that as well. So these are all starting points that can get you anywhere you want to get.
Yeah, exactly. So here I'm looking at the data folder. Once I unzip the files, as shown in the notebook, and we see we have so many different files containing the structure. And can you, Martin, talk about the parents file and the SDF file? So to clarify why
what we have is 3 files. The PDB and SDF files are interchangeable. So PDB is the protein data bank format. These are the molecules in the format that you can just concatenate with your protein, and they work. Perhaps you may need to change the numbering. Maybe not even. And SDF is the structure descriptor format. It's the standard format for Cheminformatics. It's the format that RDKit really likes. It's a format that most of the Cheminformatics tools really like. So it's essentially two approaches. One is the structural bioinformatics one, the other one is the Cheminformatics one. The params file is something typical for Rosetta. Rosetta has been developed as a protein simulation tool, and it's still a protein simulation tool. So in order for it to understand that the small molecule is not an amino acid, you have to tell it, okay, actually it kind of is. That's the connectivity, that's how it behaves. And that's what the params file has. It tells Rosetta what type of carbon each carbon is, what type of hydrogen each hydrogen is. It tells Rosetta where the molecule is more bendy than, and so on. It's just something that docking will require later on.
Yeah, thank you, Martin. So as he described, the SDF and the PDV are interchangeable, and here we are going to use the ligand file and the params file to create a Rosetta evaluator. And then we have a protocol. I mean, there is a zillion of information about Rosetta on the internet, but the idea is that we need to create some sort of protocol to evaluate how this docking happens. So we need to give the steps for this to happen, and these are described in this protocol here. How we move things, and basically, we are not going to describe this now in detail unless there are questions appearing on the chat. But once the protocol is defined, we can create a sort of scoring function, basically, which gives you an idea of what is going to be the score of how good is this peptide or small molecule and protein receptor are happy together. And we can create different trajectories, and try this. And for example, I will just run it for a question of time 5 times in a loop. This could be, of course, parallelized somehow. And in 5 times, I'm going to create a pose out of the PDV file, and I'm going to apply basically this docking protocol and check the results. And the results are expressed in we can plot them here in a 2D plot where we see the interface energy, for example, for each of the 5 peptides. It will take a bit of time, but then here you got the interface energy as a function of this is the mean square. Yeah. Okay. So, and you see, okay, which one should we keep? Which one should we submit? Because what we need to submit to Zindi is a PDV file, okay, containing both the small molecule, the drug, and the peptide. And the receptor. And let's pick the one that has the least interface energy. And in this case, is the number 0 because they are sorted by the interface energy. But we can keep as many. We can keep as many as we want, and we can basically create PDV files as many as we want and submit as many as we want. And so we can, let's go to the output folder where these 5 trajectories that I just created were generated. And let's pick one. I mean, I know this is locally on my folder, but imagine you're working on a Google Colab. Let's download it. So here we have the PDV file describing this. And so now let's go to the Zindi platform. And let's go to submissions. And let's submit a challenge. And so what we are going to do is we are going to take the file and we are dropping it into the platform. And then we are going to say, third trial. I tried 3 times today, but you can put a more sensitive name and you submit it. Okay? And we have a protocol also based on Rosetta that is going to score. Basically, it's going to measure that interface energy, maybe with a bit more like beefy machines, and like it will be run more tests on top of it, and we are going to try to score them. While maybe Martin wants to describe how we evaluate this from a PDV file. The only thing I would like to show is how this system will work. And what is happening is that Zindi, once you submit the file, is going to an API that is hosted by InstaDeep, and is running all these checks as a workflow, and then sending back the result to Zindi. And in a few minutes, it takes more or less 8 minutes to generate the score, you will get back the score, in this case, myself. Martin, would you like to talk more about how we evaluate this?
Yes. So the evaluation is intentionally a bit black boxy because one thing is that we want to avoid the evaluation system being gamed. Second, the evaluation is being updated continuously because, well, as you are learning how to do things, we are learning more and more about leishmaniasis. Because not only each of your inputs is being evaluated, but it also forms a basis for our knowledge. So we learn what works, what doesn't work. We will be doing an analysis of off-site effects. So how the molecules that you submit affect human proteins, how they affect human microbiome, and all of these will be incorporated into the scoring function. One thing that I want to stress is that even though it makes our life much easier, if you submit a beautiful pose with the ligand, with the small molecule being perfectly placed in the binding pocket and everything being well relaxed and well optimized, you don't need to, because the scoring function does that for you. So all that you may want to do is you may just want to concatenate to the ligand and the protein, and we'll take it from there. However, it's quite likely that you will spend more effort on optimizing your post than we will. So if you can submit the best post you think of, or the best post that you found by your docking, that makes life easier because we'll be taking that into account as well. Right. So the evaluation will be at the moment. The evaluation will be done with Pyrosetta for the with Rosetta and Pyrosetta for the target, for the designated target. But we will be doing the Bina-based evaluation for off-target effects. Because, well, we don't. The reason is that Bina is faster, and we don't want. We want to be able to evaluate as many off targets as possible, rather than. So we will not be. So we will be penalizing. We'll be scoring the molecules that have off-target effects a bit lower, if and only if the off-target effect is very, very prominent. So it's not something that we want you to worry about. It's just something that we want to make sure that that the submissions are valuable for the general community, for the NTD community as well. Because otherwise, you could. Because we know it's not difficult to find something that kills the parasite at all. It's just difficult to find something that kills the parasite but doesn't kill the patient. So, hence the evaluation of the off-target effects. Okay.
Okay. Do we have any other question? I think that it was a lot of information today, and yeah, we should let the things settle a bit and maybe organize a second section with more hands-on and directly talking about code once people have their Pythons working and all their Jupyter notebooks and Rosetta all in place.
Yes, I want to re-emphasize that we do have an operational Slack channels, and please do use them. Please ask questions. We are actively looking for more people to participate as experts, as guides, to answer your questions. But in order to have those people participate, we need to have questions to answer. And I'm pretty sure you have questions that need answering.
Absolutely. If anyone has any questions, the link to the Indaba community Slack will be posted again. The invitation will be posted again on our Twitter.
Actually, we have a question from Usamuddin. Would you clarify if the evaluation will be affected with by Rosetta or Autodoc Vina?
The answer
That's all the answer.
Okay, perfect.
Right. So, as I was saying, if there is any questions, do not hesitate. ping us. We're on the Indaba community Slack. There's a channel called Grand Challenge, obviously. So you can send us any questions there. If you're someone who wants to mentor, please do also let us know. We are on Twitter, on Facebook, everywhere as usual. Echo, do you have anything you would like to add as to how the Zindi platform, if there's anything that we need to know in the submissions, waiting times, things of the sort?
Nothing more from my side, I think, and I think we went through the details. So thank you very much to Nicholas and to me.
Awesome. So thank you everyone for your questions and for joining this this session. We'll have another one hopefully really soon. So yeah, find the link to the Indaba community Slack on our Twitter, and we'll see you guys next time. Thanks everyone.
Thank you.
Have a nice day. Stay safe.
Thanks
Bye.
a lot. Yeah, talk soon. Bye-bye.
Bye.
Thank you.